Okay, Pathways problem 3.42 from the book. This one's all about finding empirical formulas from measured data. I think this kind of problem's sort of fun, actually, because it's kind of investigative in nature. You might go into lab and collect some data about how many moles or how many grams of different elements are present. There's a number of different ways to do that. Your book outlines some of them. And then you sit down with that data. You try to figure out what that compound's formula was. Now, it turns out from just mass data or moles, you can't really figure out what the actual molecular formula is, okay? But you can figure out the ratio with which the elements combine, the simplest whole number ratio with which the elements combined. And that is what the empirical formula is all about. Okay, so you've heard that before, hopefully, by this point. The empirical formula is just finding the simplest whole number ratio that elements combine to make a compound. It doesn't need to be the actual molecular formula. It just expresses the ratio of the elements combination. So let's dive into this problem and see what they look like. There's a number of different variants of these you'll see in the book, but it's another potential problem you can see on an exam. It's common to this section of the class, okay? So 342A gives us the fact that we analyze a compound in lab, and we find that within that sample that we analyzed, we had 0.063 moles of chlorine atoms and 0.22 moles of oxygen atoms. So this is a composition. What made up that compound after analysis? We want to figure out what the formula is, the empirical formula. So let me ask you this. Would it be valid for me to write Cl 0.0630 0.22? I think it's kind of yes and no, right? Do we usually write formulas with fractional decimal values? No, so we're going to have to fix that, okay? But the good thing about this formula is it does accurately represent the ratio in which these elements combine. It's just that we don't like to have these sort of dirty decimal numbers down here. We like whole number, integers, right? So maybe we can fix that. There's a really simple mathematical technique to fix it. The way it works is you find the smallest number. Here that's 0.063. Look at all the numbers involved. Find the smallest and divide the smallest by itself. The reason why you do that is because this ratio is always 1. Okay? The ratio becomes 1, you have 1 Cl. You make that an integer, basically. Okay? Usually we don't show the ones in the equation. Now we also do the same thing with all other elements. So the oxygen's 0.22. We're going to also divide that by the 0.063. You have to divide it by the same number, the 0.063, the smallest one. You can't divide it by itself. You'll get 1 for everything. That doesn't make sense. Divide it by the 0.063. Okay? So all the other elements, you take their mole quantities, divide by the smallest. Okay? Everybody see that? Now let's see. Let me do that on my calculator real quick here and see what I get. Equals 0.22 divided by 0.063. It yields 3.49. Okay, so 03.49. So CL1 03.49. Are we done? No, we're not. Okay, because this is still an ugly decimal digit. We need to clean that up a little bit. Okay. Now, when you get to this point, after you divide by the smallest and one of the values in the integer, usually you can maybe envision a pathway that you can clean this formula up relatively easily and make it into an empirical formula with whole numbers as subscripts. So I look at this and I say, okay, it's a 1 to 3.5 ratio right now. Right about 3.5. What if I made this a 2 and I also doubled this one? Wouldn't it be a 2 to 7 ratio, which is the same as the 1 to 3.5? I think it would. And that would be my empirical formula. So after you divide by the smallest number, you usually get to this point where you can kind of find a solution to reason your way through. In this particular case, if we double both of them, we get a 2 and a 7. And that's our empirical formula for this particular compound, okay? So that's how to come up with an empirical formula from elemental data, all right? Now, this problem goes on and gives us a couple more examples that I also want to turn our attention to. The framework for them are going to be pretty much the same, but they will be worked slightly differently because slightly different information is going to be given in each case. In part B, I'm told that I've got 2.45 grams of silicon that results from a compound and 12.4 grams of chlorine. So I had some compound, I undergo a chemical process test, and the data yields this number of grams of silicon and this number of grams of chlorine. So I do an analysis for what elements are present, and this is what I find, right? How do I take those masses and come up with an empirical formula for this compound? All right, now the thing that I want to catch your attention right off the bat for part B is that we're given grams. This could be a very likely data source. We might be measuring the mass of these elements in grams. It's certainly very possible that we are. But do grams, units, describe the whole number ratio that atoms combine to make molecules? I argue that they do not. There might be a fixed mass ratio between elements when they combine, and we know that that's the case, but it doesn't describe the number ratio that the atoms combine in, and that's how we write formulas. So the thing is if we're having gram units, we need to get rid of those units right away. We need to convert them to moles, okay? Because moles is our base counting unit. So what I'm going to do then for each of these is I'm going to convert to moles. And if you're ever given gram units in one of these problems, boy, you need to convert to moles right away, okay? It's a very, very standard thing to do. So I have to go to my periodic table, and I need to look up for silicon. I've got 28.09 grams per mole. I go look at my box for chlorine. I've got 35.45. And I'm in business. I can do that computation. When you do the math, you find that you've got 0.0872 moles silicon, and I've got 0.3497 mole of chlorine. Okay? All I've done, converted mass to moles. The whole strategy there is moles are counting unit. So I think then I could write formula of sorts for this compound as Si subscript 0.0872 Cl 0.3497. But again, we don't like to write formulas for compounds with non-integer numbers, generally speaking. So we probably want to clean this up. Now, the cleaning up protocol is exactly what we've described for the part A. You find the smallest number, divide all other numbers by it to find the whole number ratio that represents the empirical formula. In this case, the smallest number is that for silicon, the 0.0872. As a result, this becomes 1. I also need to divide the 0.3497 by 0.0872. And if I do the division on that, it turns out that that ratio is approximately 4. So our empirical formula is SiCl4 for this compound. Now when you're working these problems on your calculator, when you do these ratios, you might not get exactly 4, but generally speaking the result is pretty close. In other words, you might not get exactly 2, 3, 4, you might not get exactly the integer value, but generally speaking the result is pretty close to an integer or a half integer like we saw in part A, okay? And if you get that situation, that tells you that you're able to round. Usually what the authors of these problems do is they build into it a little bit of uncertainty. This would theoretically be based on measurement data, which would have some uncertainty associated with it. So this rounding is generally encouraged, okay? But generally a slight rounding, okay? If you get a ratio here, if this was ratio 3.72, then that wouldn't really be close enough. But if it was 3.97, that's full, okay? So hopefully you kind of get a feel for that. Nonetheless, that's part B here. Moving on. Let's talk part C. In part C, I'm told that a compound is 27% carbon by mass and 72.7% oxygen by mass. And I'm asked, what in the world is the empirical formula? So I'm given mass percent composition data, and I'm expected to write the formula. And this is a little bit different because I don't have the number of moles of each element. I also don't have the number of grams of each element, so I can't find moles right off the bat here. But I know that whatever compound this is, it has this ratio between these two elements, okay? So, I guess I could try trial and error and see if I can come up with a match, but there's a better, more structured way to do it. And you say, wow, there's no data given. This is one of those problems where you have to make an assumption. You have to assume a certain amount of material is present, whether that be 100 grams, 1,000 grams, whatever it is. You have to assume a certain amount of material is present. And the beauty of doing that, of course, is that this mass composition remains the same. It doesn't matter how much you've got. If I've got 10 grams, 100 grams, 1,000 grams, it's always 27.3% carbon, 72.7% oxygen. It's the characteristic of the material. These numbers don't scale with the amount. So, just from experience, I know that it's awfully convenient to assume that I've got exactly 100 grams. The reason why I do that, of course, is because of the mathematics. I can then say in that 100 grams, 27.3 grams is carbon, and 72.7 grams is oxygen. You add them together, you get the 100. These numbers are consistent with the mass percents, okay? So what we've done is made an assumption of a certain amount. That's allowed us to convert into grams of different elements, right? And then we proceed the same exact way. First important thing is grams does not describe whole number ratios that atoms combine them. So we need to convert the grams into moles of each element. We do so by dividing by 12.01 and or 16, depending on which one we are talking about, which element we're talking about. That yields 2.27 moles carbon and 4.54 mole of oxygen. That's all we did. Assumed 100 grams, then convert it to moles. We do the same exact process. When we take our elements, we write subscripts describing the combination ratio, and then we clean them up by dividing by the smallest. Here that's 2.27. And I think you'll see this works out to a 1, that works out to a 2, and I've got the empirical formula for this compound, CO2. So this just shows a couple different examples of these problems. You could see one on the exam.